keeps a train on the track? Go ahead. Think about it. I bet most of you just pictured those little lips on the wheels. The flanges, those raised edges that stick out on the inside. You figured the flanges bump against the rail whenever the train starts to wander, and that keeps the whole thing lined up, like bumper rails in a bowling alley. And I want you to hold that answer in your mind. Feel confident about it, because when I show you what actually happens, the look on your face is going to be worth every minute we spend together today. See, I used to ask this question in my classes. I would walk in and say, all right, here is a train, 2 steel rails. The wheels are sitting on those rails. The whole thing is moving at 60 miles per hour. What keeps the wheels on the track? And every hand that went up said flanges. Every single one. Smart students, graduate students, some of them, they all said flanges. And they were all wrong. Not completely wrong, but wrong in the way that matters. Wrong in the way where you think you understand something, and that feeling of understanding is actually blocking you from seeing the real thing. That is the most dangerous kind of wrong in physics, by the way. Not ignorance. Confident ignorance. The kind where you stop asking because you think you already know. I would see it in their eyes. That settled, comfortable look. Flanges. Done. Next problem. And I would say, are you sure? Are you really sure? And they would nod. Some of them would even look slightly annoyed, like I was wasting their time with a kindergarten question. That is exactly when I knew I had them, because the real answer is so much better than flanges. It is one of those answers that once you see it, you can never unsee it. It changes the way you look at every train, every wheel, every curved piece of track for the rest of your life. And it teaches you something about physics itself, about the way nature solves problems that goes far beyond trains. So let us start at the beginning, the real beginning. Let us look at a wheel. Take any wheel you want, a car wheel, a bicycle wheel, a wagon wheel. What shape is it? It is a cylinder, a flat cylinder. The part that touches the ground is straight across, or close to it. When you turn the steering wheel in a car, the front wheels angle left or right, and the whole thing follows. Simple enough. Now a train wheel is different, and I want you to pay very close attention to the difference, because this is where the whole story lives. A train wheel is not a flat cylinder. If you could slice it in half and look at the cross-section, you would see that the tread, the part that actually sits on the rail, is slightly sloped. It is wider on the inside near the flange and narrower on the outside. In other words, the running surface of the wheel is not flat. It is a cone, a very gentle, very shallow cone. The taper is not dramatic. You might not even notice it if you glanced at a wheel sitting in a rail yard. But it is there, and it changes everything. Before we talk about why that matters, let me give you the problem. The real problem, the one my students never thought about until I forced them to. Look under your car sometime. Between the 2 drive wheels there is a thing called a differential. A gorgeous piece of engineering. What it does is this. When you drive around a curve, the wheel on the outside of the curve has to travel a longer distance than the wheel on the inside. If both wheels were locked together, spinning at exactly the same rate, one of them would have to skid. The outside wheel would be dragged along too slowly, or the inside wheel would be dragged along too fast. Either way, you are scraping rubber against pavement and the car fights you. The differential solves this by letting the 2 wheels rotate at different speeds. It splits the engine's power between them in a clever way so that the outside wheel can spin a little faster and the inside wheel a little slower. Hundreds of gears inside a metal housing, also your car can make a turn without tearing itself apart. Beautiful, right? A real piece of work. Engineers spent decades perfecting the differential. It is a miniature marvel of mechanical ingenuity. You have bevel gears meshing with spider gears, all rotating inside a carrier, all bathed in oil, all machined to tolerances of a few thousandths of an inch. It is one of the most important inventions in the history of land transportation, and every automobile on Earth has one. Every truck, every bus. If you have 4 wheels and an engine, you have a differential. It is as fundamental to driving as the steering wheel. Now look at a train. A train has no differential. None. Zero. Nothing. Not one gear. Not one bearing. Not one clever mechanism to let the wheels turn at different speeds. The 2 wheels on each axle are pressed onto a solid steel shaft. One piece of metal, forged or machined as a single unit. When the left wheel turns, the right wheel turns at exactly the same angular velocity. Not approximately the same, exactly the same. They have no choice. Physics does not negotiate. So how does a thing like this go around a curve? Stop and really think about that for a second. Because this is the question that should bother you. This is the question that should keep you up at night. Every car in the world needs a differential to turn. Every truck needs one. These are vehicles that weigh a few thousand pounds. A locomotive weighs 200,000 pounds, sometimes more, and it goes around curves all day long without any differential at all. That should strike you as impossible, or at the very least deeply puzzling. And by the way, the problem is even worse than I made it sound. It is not just that the outside rail is longer. On most curves, the outside rail is also higher. It is tilted. The track is banked, just like a racetrack. Engineers call it super elevation. They raise the outer rail a few inches above the inner rail, so that the centrifugal force pushing the train outward is partially balanced by gravity pulling it inward and downward. This banking is important for comfort and safety, but it means the geometry is even more asymmetric than a simple curve would suggest. The outer wheel is higher, the inner wheel is lower, and the axle is tilted. Everything is off-center, and still the train navigates it smoothly. Think about that for a second. A train comes to a bend in the track. The outside rail is longer than the inside rail. That is just geometry. A bigger arc is always longer than a smaller arc. The outside rail has to cover more ground than the inside wheel. But both wheels are bolted to the same axle. They must rotate at the same angular velocity. They have no choice. If the wheels were flat cylinders, this would be impossible without slipping. The outside wheel would need to slide forward along the rail, grinding steel on steel, or the inside wheel would need to scrape backward. Either way, you would get shrieking, sparking, metal-on-metal friction at 60 miles per hour, pulling hundreds of tons. This should be a catastrophe. But trains go around curves every day, all around the world, smooth as butter. Millions of them, some of them weighing thousands of tons, some going over 100 miles per hour. So what is going on? This is where the cone comes in. Remember that gentle taper I told you about? The tread of the wheel is not flat. It slopes. The diameter of the wheel is slightly bigger on the flange side, the inside edge, and slightly smaller on the outer edge. Now watch what happens when the train drifts a little bit to one side. Let us say the whole axle shifts slightly to the right. The right wheel moves outward, so the rail contacts a part of the tread with a smaller diameter. Meanwhile, the left wheel moves inward, so the rail contacts a part of the tread with a larger diameter. Both wheels still spin at exactly the same rate, same axle, same rotation, but the left wheel is now effectively a bigger wheel, and the right wheel is now effectively a smaller wheel. What happens when you have a bigger wheel and a smaller wheel on the same axle spinning at the same speed? The bigger wheel covers more ground per rotation. The smaller wheel covers less. So the axle starts to curve. It curves to the right, the very direction it needs to go to get back toward the center of the track. This is not a subtle effect. You can calculate it. If the taper angle is such that the diameter changes by 1 millimeter over the width of the tread, then a lateral shift of just a few millimeters produces a measurable difference in rolling radius. And that difference, multiplied by the rotation rate, gives you a real steering force. Not a suggestion, not a gentle hint, an actual force that pulls the wheel set back towards center. The mathematics is almost embarrassingly simple. The circumference of a circle is pi times the diameter. Bigger diameter, bigger circumference, more distance covered per revolution. If the left wheel has a diameter that is even 2 millimeters larger than the right, then in one full revolution the left wheel covers about 6 millimeters more ground than the right. That does not sound like much, but a train wheel makes many revolutions per second. At 60 miles per hour, a typical wheel is rotating about 8 times every second. That means the left side is gaining nearly 50 millimeters per second on the right side. 50 millimeters per second of differential motion is a real curve. It adds up fast. And it does not stop there. If the axle overshoots and drifts a bit to the left, the exact same thing happens in reverse. The right wheel is now riding on a bigger diameter, the left on a smaller, and the axle curves back to the right. The train is steering itself. No gears, no mechanism, no computer, no driver input, just geometry. The shape of the wheel does all the work. I want you to appreciate how remarkable this is. An automobile needs a differential with dozens of precision gears to handle the speed difference between inner and outer wheels on a curve. A train handles it with a slope, a taper, a surface that is not flat. That is the entire mechanism. The solid axle, which looks like a problem, actually becomes part of the solution. because the axle forces both wheels to rotate at the same angular speed, and the coning converts that equal rotation into unequal linear speeds. The problem is the solution. Let me say that again because I think it is extraordinary. The shape of the wheel does all the work. A simple taper, a cone you would barely notice with the naked eye, gives the train a built-in correction system. Drift left, the geometry pushes you right. Drift right, the geometry pushes you left. The train snakes along the track in a gentle wave, always correcting, always coming back to center. And the flanges, those lips everyone thinks are doing the work, they almost never touch the rail. In normal running, on a straight track or a gentle curve, there is a gap between the flange and the rail. The flange is the emergency backup. It is the guardrail at the edge of a cliff. It is there for when something goes really wrong. If the lateral displacement gets too large, if the coning cannot correct fast enough, the flange catches the rail and forces the wheel back. But in normal operation, the flange is just sitting there, not touching anything. Most people have the whole picture backwards. They think the flanges are the primary system and the wheel shape is just some manufacturing detail. It is the exact opposite. The conical tread is the primary guidance system. The flange is the last resort. Now you might be saying, okay, fine, the cone helps the train steer on curves, but what does that have to do with staying on the track on a straight section? Excellent question. Here is the beautiful part. On a perfectly straight track, if the axle is sitting exactly in the center, both wheels have the same effective diameter. They cover the same ground per rotation. Everything is balanced. The train rolls straight. But tracks are never perfect. There is always a tiny bump, a slight imperfection, a gust of wind, a joint in the rail that gives the axle a nudge. The moment the axle shifts even a tiny amount to one side, the coning activates. One wheel gets effectively bigger, the other gets effectively smaller, and the axle starts to curve back. It overshoots, it passes through the center and goes a tiny bit the other way. The coning kicks in again in the opposite direction. The axle curves back, it overshoots again. What you get is a sinusoidal path, a smooth, gentle wave. The axle oscillates back and forth across the center line, never straying far, always correcting. This wavering path has a name. It was worked out mathematically by a German engineer named Klingel back in the 1880s. The wavelength of that oscillation depends on just two things: the distance between the wheels and the steepness of the cone. That is it. Two geometric parameters determine the entire guiding behavior of every standard gauge train on the planet. Now, I want to make sure you understand what I mean by wavelength here, because it is not the same as frequency. The wavelength is a distance. It is the distance along the track that the wheel set travels to complete one full side-to-side cycle. One sway to the left, one sway to the right, back to center. That is one wavelength. For a typical freight train wheel with a diameter of about 33 inches and a standard conicity, the Klingel wavelength is somewhere around 30 to 50 feet. That means for every 30 to 50 feet of track the train covers, the axle completes one full oscillation. At low speed, that oscillation might take a full second or two. At high speed, the oscillations come faster because you are covering those 30 to 50 feet in less time. And here is the key: the wavelength does not change with speed. It is purely geometric. Speed only affects the frequency, how many oscillations per second. The spatial pattern is fixed by the cone and the gauge. That is a beautiful result because it means the self-correction is always the same, whether the train is creeping along at 5 miles per hour or racing at 100. Think about that. Two numbers, the gauge of the track and the taper of the wheel. From those two numbers you get a self-correcting guidance system that works automatically at any speed, requires no moving parts, has no electronics, no feedback sensors, no actuators. It is one of the most elegant pieces of engineering in human history, and almost nobody knows about it. Let me push on this a little more because there is something here that connects to deep mathematics. The motion of the wheel set, this gentle oscillation back and forth, is what physicists call simple harmonic motion. It is the same kind of motion as a pendulum swinging, or a mass on a spring bouncing up and down, or a plucked guitar string vibrating. The restoring force, the force that pushes the wheel set back to center, is proportional to the displacement. Move a little, get pushed back a little. Move a lot, get pushed back a lot. That linear relationship between displacement and restoring force is the hallmark of harmonic oscillation, and it shows up in every corner of physics. When I first realized that a train on a track is a harmonic oscillator, it made me laugh. because a harmonic oscillator is the first thing you study in physics. It is the simplest system there is: mass, spring, motion, and here it is hidden inside a machine that weighs hundreds of tons and stretches half a mile long. The universe loves its simple systems. It keeps using them over and over, just dressed up in different costumes. Let me give you a picture that might make this even clearer. Take a paper cup, an ordinary disposable cup that is wider at the top and narrower at the bottom. Lay it on its side on a table. Give it a push. What does it do? It rolls in a circle. It does not go straight. It curves toward the narrow end. Why? Because the big end covers more distance per rotation than the small end. The big end is like the wheel riding on a larger diameter, and the small end is like the wheel riding on a smaller diameter. The cup naturally turns. Now take two paper cups and tape them together, bottom to bottom. You get a shape that is wide on both ends and narrow in the middle, like two cones joined at their tips, an hourglass shape. Put that double cup shape on two parallel rails, like pencils. Give it a nudge. It wobbles back and forth, but it stays on the rails. If it drifts to one side, the effective diameters change. It curves back, overshoots, curves back again. The same sinusoidal dance. That double cup shape is a rough model of a train wheel set. In fact, if you flip it around so the wide parts face inward and the narrow parts face outward, you have an even better model. That is actually what a train wheel looks like. The bigger diameter is toward the center of the track, and the smaller diameter is toward the outside. When the axle shifts, the inner wheel rises to a bigger part of the cone, and the outer wheel drops to a smaller part. Self-correction. You can try this at home. It takes about 2 minutes and a couple of cups, and you will see the physics with your own eyes. Use two pencils laid parallel as your rails, about 6 or 8 inches apart. Tape two cups bottom to bottom and lay them across the pencils so they can roll. Give them a nudge. Watch what happens. They wobble, they weave, but they stay on the pencils. Do the same thing with a flat cylinder like a soup can, and it will roll right off the edge. Here is something wonderful. This same principle was known to barrel makers centuries before anyone built a railroad. Traditional wooden barrels are fatter in the middle and narrower at the ends. That is the cooper's art. And one of the reasons for that shape, beyond holding the staves together, is that barrel-shaped containers can be rolled along wooden rails in a warehouse. Workers would lay 2 planks on the ground, set the barrels on their sides on the planks, and roll them from one end of the building to the other. Because the barrel is fatter in the middle, it self-steers. It weaves slightly, the same sinusoidal path, but it stays on the rails. You can see this in old photographs and films of breweries and shipping warehouses from the 1800s. Barrels rolling on wooden rails, wobbling gently, never falling off. The coopers did not know they were exploiting conic section geometry. They just knew that barrels with a belly stayed on the rails and straight ones did not. Practical knowledge arrived at through trial and error, centuries before anyone wrote down the physics. That is the way things often happen. The practice comes first, and the understanding comes later. The railroads used conical wheels for decades before Klingel wrote down the mathematics. The barrel rollers used bellied barrels for centuries before anyone thought about restoring forces in harmonic oscillation. Nature's principles are there whether you understand them or not. Understanding just lets you use them more deliberately. All right, so here is where it gets more interesting. Because you might think, great, the cone fixes everything, trains are perfect, end of story. But nature is never that clean. There is always a catch. Remember that sinusoidal oscillation I described, the axle wavering gently back and forth? At low speeds, that oscillation is damped. The energy in the side-to-side motion gets eaten up by friction and the stiffness of the suspension. The wavering dies out. The train settles into a smooth ride. You barely feel anything. But as the speed increases, something changes. The inertial forces in that oscillation grow. The mass of the wheel set swinging side to side generates more and more lateral force with each cycle. At some speed, the energy being fed into the oscillation from the forward motion of the train matches the energy being dissipated by friction and damping. The oscillation stops dying out. It sustains itself. Go a little faster, and the energy input exceeds the damping. The oscillation grows. Each swing is a little bigger than the last. The axle swings wider. The forces get stronger. The swing gets wider still. This is a positive feedback loop. The technical term is hunting. Hunting oscillation. The name is perfect, actually. The wheel set is hunting for the center of the track, swinging back and forth, searching, overshooting, searching again, like a dog sniffing for a scent, running left, running right, unable to settle. That restless seeking is what the engineers saw when they first observed it, and the name stuck. The physics of hunting is remarkably similar to a phenomenon that destroyed aircraft in the early days of aviation. Engineers called it flutter. An airplane wing at a certain speed would begin to oscillate. The oscillation would feed on itself, growing larger with each cycle until the wing tore off. Flutter killed many pilots before engineers figured out how to suppress it. And the mathematics that describes flutter and the mathematics that describes hunting are nearly identical. Two coupled motions exchanging energy, feeding off the forward velocity, growing until something breaks. That is not a coincidence. It is the same physics, the same equations. Whether it is a wing in an airstream or a wheel set on a rail, the underlying structure is the same. Energy from forward motion gets converted into lateral oscillation, and if the damping cannot keep up, the amplitude grows without bound. You have probably felt this if you have ever been on an old train going fast. That rhythmic lateral rocking, that side-to-side lurch that makes you grab the armrest. That is hunting. The wheel set is oscillating with growing amplitude and the car is rocking with it. And here is where the flanges suddenly matter. When the oscillation gets big enough, the flange slams into the rail. Hard. There is a sudden jolt, a bang of steel on steel. The wheel rebounds. It swings the other way, and the opposite flange slams. The train lurches violently. Forces spike to enormous levels. The rail gets shoved sideways. The wheel gets battered. Bolts loosen. Components fatigue. If you have ever stood near a track when a heavy freight train passes at speed and heard that rhythmic banging, that ka-chunk, 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 you might have been hearing hunting. The flanges hammering the railheads over and over, dozens of times a second. This was a genuine mystery in the late 1800s. Trains were getting faster, and at a certain speed they would start shaking themselves to pieces. Rails were damaged, wheels were destroyed, cars derailed. Nobody quite understood why. The problem was first noticed around 1880, 1890, when train speeds began to push past 50 or 60 miles per hour regularly. Before that, trains were slow enough that hunting was either absent or so mild nobody cared. But as the railroads pushed for speed, pushed for schedule, pushed to connect cities faster, they hit this invisible wall. Above a certain velocity, things fell apart. Think about what was happening. The very feature that keeps the train on the track, the conning of the wheels, was also the thing that could tear it off the track at high speed. The same geometry that produces gentle self-correction at 30 miles per hour produces violent oscillation at 100. The restoring force and the destabilizing force come from the same source. This is not unusual in physics, by the way. Many systems that are beautifully stable in one regime become wildly unstable in another. A pendulum hanging straight down is perfectly stable. Flip it upside down and balance it on its tip, and it is wildly unstable. Same pendulum, same forces, different regime. Or think about a bicycle. At walking speed, a bicycle is almost impossible to keep upright. You wobble, you overcorrect, you fall over. At a brisk riding speed, it practically steers itself. You can ride with no hands, and it just goes. The physics that creates stability at one speed creates instability at another. The speed changes the balance between competing forces, and below a certain threshold, one force wins. Above it, the other force wins, and the transition can be sharp, almost sudden. The hunting problem plagued railroads for decades. The speed at which it appeared was called the critical speed, and for much of the early 20th century it put a hard ceiling on how fast trains could go. The solution, when it came, involved the suspension. Engineers figured out that if you could add damping, if you could put shock absorbers and carefully tuned springs between the axle and the car body, you could absorb the energy of the oscillation before it built up. You could push the critical speed higher, and that is exactly what happened.